Problem 12. The prime factorization of a natural number. That's just, you can kind of view that as positive integers. Sometimes they'll throw 0 in the natural number definition, depending on what context you're working in. But the prime factorization of a natural number n can be written as n is equal to pr squared, where p and r are distinct prime numbers. Fair enough. How many factors does n have, including 1 n itself? Well, they're saying that this is some natural number that can be written this way. Let's just pick one example. So if we just set p, I'm just going to pick some prime numbers here. P is equal to 2 and r is equal to 3. Then n is equal to p times r squared times 3 squared, which is equal to 2 times 9, which is equal to 18. This is just one instance, one n that satisfies these conditions. I could have picked 5 and 7, or I could pick 3 and 2, but all of them should have the same answer, because that's what this question is implying. So this is a possible n, and then how many factors does it have? Let's factor it out. It's got 1 and 18, 2 and 9, 3 and 6. So it's got 1, 2, 3, 4, 5, 6 factors. So the answer is D. And you could try it out with other numbers if you like. Make p equal to 3 and make r equal to 2. Then you'd have 3 times 2 times 2. You'd have the number 12. And you'd see its factors are 1 and 12, 2 and 6, and 3 and 4. So you'll see the same thing, exactly 6 factors. Problem 13. Given Pn is equal to 150, where p is a prime number and n is a natural number, which of the following must be true? So let's just think about it. What are all the possible values for p? To do that, we'd have to figure out the prime factorization of 150. I'll do that in black. So 150, let's do its prime factorization. That's 2 times 75. 75 is 3 times 25. 25 is 5 times 5. So 150 is equal to 2 times 3 times 5 times 5. That's its prime factorization. So p could be any of these numbers. So for example, p could be, if p was 2, then n would be 3 times 5 times 5. If p were 3, then n would be 2 times 5 times 5. If p were 5, then n would be 2 times 3 times 5. Right? Let me write this, make this a little bit clearer. These are my p's, because p has to be one of the prime factors of 150, and then n is whatever's left over when you divide by that p, right, in each of these cases. So let's look at the choices. Which of the following must be true? P is a factor of either 10 or 15. Let's see, 2 is a factor of 10, 3 is a factor of 15, 5 is a factor of both 10 or 15. So that actually looks like the correct answer. Let's write that. Let's square that right now. Let's look at the other choices just to make sure we haven't missed anything. 10 is a factor of n. Let's see. Over here, well, no, 10 is not a factor of this n. 3 times 5 times 5 is 75. 10 is not a factor of this number, so it's not going to, 10 is a factor of these two choices, but this is a possible n right here. 75 could be n, so this is not the correct answer. N is a factor of either 10 or 15. N is a factor. Remember, these are our n's right here. These are the potential n's. This is not a factor of this is neither a factor of 10 nor 15. 10 or 15 are smaller numbers than all of these over here. And then, so this is not the answer. And then 15 is a factor of n. 15 is a factor of n. So in order for 15 to be a factor, you have to have a 3 in there. And you look at this choice right here. 2 times 5 times 5. This is 50. This n right here is 50. 15 is not a factor of 50. So our first inclination was correct. P is a factor of either 10 or 15. Next problem. Next problem. All right. The greatest common factor of n and 540 is 36. Which of the following could be the prime factorization of n? So let's just think about this a little bit. The greatest common factor of n and 540. So the largest number that goes into both 540 and this mystery number n is 36. Which of the following could be the prime factorization of n? Let's just take the prime factorization of everything, just so we can kind of go down to the most digestible parts. So the prime factorization of 540, let's see, 2 times, what is it, 270. This is the same thing as 3 times 90, and 90 is 3 times 30, and 30 is 3 times 10. 10 is 2 times 5. So the prime factorization of 540 is equal to, there's two 2's here, so it's equal to 2 squared times 3 to the third times 3 to the third times 5. That's 540's prime factorization. Now, the greatest common factor of n in 540 is 36. 36 is equal to what? I'll do it right here. 36 is 2 times 18. That's 2 times 9. And that is 3 times 3. So 36 is equal to 2 squared times 3 squared. So n has to be some multiple of this that does not that is not still go into 540. Let me show you what I mean. Let's see which of these could be possible prime factorizations of n. So a is 2 times 3 squared. Well, that doesn't work because, remember, n, this right here, 36 has to be divisible into our n. 36, or 2 squared times 3 squared, is not divisible into this because we don't have a 2 squared here. So a is not our choice. I'll do it in red when I knock out choices. So a is not our answer. 2 squared times 3 squared. This is tempting because 36 definitely goes into 2 squared times 3 to the third. Sorry, this is 2 squared times 3 to the third. 2 squared times 3 squared definitely goes into that. In fact, it goes into it 3 times. This is 36 times 3 right here, right? Because the difference between this number and this number is the power of 3, and this one has a higher power of 3. So 36 definitely goes into this number, but we have to be very careful. This number right here also goes into 540. If n was this number right here, then n would go into 540 because this is 2 squared times 3 to the third, 2 squared times 3 to the third. Then the greatest common factor of n in 540 would be this instead of this. So this can't be our answer because if this was our n, then n would be the greatest common factor of n in 540. So this can't be our choice because this is actually a larger number that goes into 540 than this one right here. Let's look at choice C. 2 to the fourth times 3 squared times 7. This looks good because 36 definitely goes into this number. 2 squared definitely goes into 2 to the fourth, goes into it 4 times. 3 squared definitely goes into 3 squared. And then we're multiplying it by 7. And what's good about this is we're multiplying it by a number or a factor that's not in 540. So this looks like our best choice right here. This looks like our best choice. Let's look at the last choice just to make sure we haven't missed something. 2 to the fourth times 3 to the fifth. This part right here is definitely a multiple of our greatest common factor. So it looks good so far. But then we do it times 5. Times 5. If this was our n, if this right here was our n, then the greatest common factor of this number in 540 would not be 36. It would be, let's see, we would have 2 to the squared, because that's the largest power of 2 that goes into both of them. It would be 2 squared times 3 to the third times 3 to the third, right? Because that's the largest power of 3 that goes into both, times 5. This would be the greatest common factor of this number in 540 is this, which happens to be 540. So it can't be this choice right here. And again, you can use the same argument on choice B. The greatest common factor of choice B and 540 is 2 squared times, because 2 squared goes into both numbers, times 3 to the third, which is a very different number, or not a very different number. It's 3 times 36. So that's the other rationale for why B is not a legitimate answer. Next problem, 15. You scroll down a little bit. A shipping container. A shipping container measures 8 feet by 12 feet by 24 feet. Let me draw that. So we have 8 feet by 12 feet. And then it's 24 feet, just like that. 24 feet. So maybe it looks something like that. That's actually what shipping containers really do look like. Looks something like that. The container is to be filled with identical cube-shaped boxes, each having sides measuring a whole number of feet. Which of the following expressions represents the smallest number of such identical boxes that could be packed into the container with no empty space remaining? So they say the smallest number of identical boxes, which means we need the biggest possible boxes that can be fit, cubic boxes that can be fit into this container with no space. So the dimensions of those boxes have to be the greatest common factor of 8, 12, and 24. So we could write this right. The dimensions, or let me say the box side, has to be equal to the greatest common factor of 8, 12, and 24. So what's the biggest number that goes into 8, 12, and 24? You can do this from inspection. It's 4. And you can verify that. If the boxes were 4 on a side, then in this dimension you'd fit 8 divided by 4 of them, or 2 of them. So you'd have 1, 2 boxes in that dimension. In this dimension over here, you would have 3 of them, right? 12 divided by 4, you'd have 3 boxes in that dimension. And in that dimension, you would have, let me draw these just like that. You would have 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. You would have 6, or 24 divided by 4. So if you want to know the total number of boxes you fit, and I'm just looking at the choices, they didn't actually do the math. They say, well, in this dimension, I have 8 divided by 4 boxes. In this dimension, I have 12 divided by 4 boxes. So times 12 divided by 4. And in this dimension, I have 24 divided by 4 boxes. 24 divided by 4. So that's how many boxes we can fit. We could multiply it out, but this is actually one of our choices right there. So the whole key is just realize, well, look, I'm trying to pick if the boxes have to be cubes and there's no remaining spaces, the dimension of the boxes has to be divisible into all three of these numbers. And I want the biggest possible dimension because we want the smallest number of boxes. And that's where we got the greatest common factor of 4. And then you say, okay, 4, and if we have boxes of dimension 4 feet, then in this direction we're going to be able to fit 8 divided by 4, this direction 12 divided by 4, and this direction 24 divided by 4.